right, hi everybody. I realize it's mid-afternoon and you guys, your lunch is fully processed and I'm standing between you and the coffee break, so I'm gonna try and move things along. We're right on schedule though. The reason I wanted to talk about this talk is a little bit different maybe than some of the other talks you've heard today. Because it's a little bit more general interest. Like many of you, I have been exposed a little bit to ASIL-B and ASIL-D throughout my career, and I knew it was difficult, and you hear things like dual-core lockstep. But then I also have my Roku at home that every now and then freezes up, and I wonder, what is it about, you know, my wife's new car with the lane keeping assist? What's gonna prevent it from going haywire like some other systems with complex hardware and software. So I'm going to talk a little bit about, you know, some of the requirements for automotive safety, ASIL-D, why is it difficult? Why is it more than just dual-core lockstep? Talk about certification. That's a big, you know, it sounds complicated, and it is complicated, but it's easy to understand. And then how it's not just about the CPU. Of course, I work for Andy's. What we do is solve the CPU part, but it's also our job to enable you SOC designers to solve the total system problem. So the interesting thing about complex hardware and software is that stuff fails, right? Sometimes it fails because of systematic faults, which is just a fancy way of saying somebody designed it wrong and there might be bugs in it, either the hardware or the software, so you have to think about both. On the right side is also random faults. So every now and then you get a bit flip or you get a flop that flips from a 1 to a 0. And you have to solve for that as well because, again, you don't want your car locking up like your Roku, right? No offense, I love my Roku. If there's any Roku employees in the house, I think it's great. So we have to solve for all of this, and it's actually quite difficult. So this is just a quick note. So ASIL-D is the highest level. That's going to be your anti-lock braking systems, blah, blah, blah. And that SPFM, single point failure metric, means that we have to cover more than 99% of the possible places within your system where there can be a single fault. An individual bit flip has to be covered 99% of those possibilities throughout your system. And that's not just the CPU subsystem. And I colored it red at the bottom to say that ASIL-D is really, really difficult. ASIL-B is hard. ASIL-D is really, really difficult. And that's why we use things like dual-core lockstep. Dual-core lockstep is extraordinarily expensive, right? You're basically saying, I've got a CPU, it's the core of my system, and it's so difficult to get coverage, I'm willing to put an entire second one there to do no more processing whatsoever. I'm just doing the same processing twice so that I can detect when there's a difference. That's expensive, right? But it's worth it because you don't want your anti-lock braking system locking up while you're driving down the freeway. And it's easy to think about dual-core lockstep. It's just what I explained, right? It's, I've got two, I want to detect when there's a difference. Ideally, as you can see in the picture, you actually want to time shift the two cores. It doesn't have to be by a lot, just a couple, 3 cycles, so that if something affects one in time, say there was a glitch on the VDD rail, it doesn't affect the other one in exactly the same way. So ideally, you want to time shift that. Also, ideally, you would actually want to lay out those two cores separately, right? Because what if you had a vulnerability where some part of the circuit was vulnerable to some sort of a failure? You wouldn't want that vulnerability to happen twice in the same place, because if they both fail the same way, you didn't detect the failure, right? In Andy's cores, we also have additional protection, which is an inactivity monitor, which sounds simple, but it's actually very, very important. I realize I'm harping on Roku, but if it does lock up or it freezes, how would you know? So we have an inactivity monitor in case, and that could be because I have some sort of a larger system bug where both of my cores lock up because I don't know, PCIe or some other subsystem has a problem. So I can detect that that is happening. So you can sort of sensitize the whole system to these sorts of failures, signal that's an error. And by the way, you don't actually necessarily need to recover in hardware from these problems. You just need to, the system needs to know that there is a problem so that it can disable, contain the issue so that, for instance, if your lane keep assist doesn't actually assist, it turns off. That's better than it deciding that it needs to make a hard left or a hard right. That would be bad. So it really just needs to detect that there's an issue so that it can take recovery measures. And potentially that's just a light on the dashboard, take it in for service, or it could be, and I've had this happen on my car, it wasn't luckily on the main display, but on the infotainment display, while I'm driving down the road, it stops, reboots, comes back up, continues. It actually remembered the course that I was on. But that's a little disconcerting when you're driving down the road because the screen goes blank and you realize, oh, this is like what happens to my computer sometimes. That's bad. All right. I talk about dual core lockstep. I think most of you will probably realize that you also want to have ECC on your memories because memories represent the most storage on any given chip, almost certainly any given chip. And those bits are sensitive. They're sensitive because TSMC and every manufacturer in the world plays tricks to make sure that the memories are as small as possible. And those tricks means that under normal operating conditions, those bit cells are very, very stable. But they're sensitive to single event upsets. We solve that by adding parity and enough parity to get single error correction, double error detection. You actually may or may not need the correction part of it. That's kind of up to a larger system decision. But you almost certainly want to report when there is an issue. You might also want to report if it's been corrected so that the larger system can start to track that. For instance, if you start to get many corrections, that's indicative of an imminent larger failure. You also would like to ideally scrub your memories, which just means going through systematically and if you're doing correction, you're just doing reads of each location so that any latent faults can get corrected. The reason you do that is because if you have double error detection, you can't correct double errors. And if you get 3 errors, you can't even detect those. Those might look like single bit errors or double bit errors. If they stack up and you get to more than double bit errors, that's undetectable, that's really bad. So you want to scrub them from time to time so that you don't get these failures stacking up. Okay, I added this slide. This is really only applicable to ASIL B systems. So ASIL B systems typically do not have that dual core lockstep, but they will have ECC. ECC is incredibly important. But if you think about ECC, what happens if you have a fault in the ECC correction logic itself? If you had one of those, all of that coverage on your RAM, which is a lot of your coverage, is potentially gone if you had a fault there. So there's actually an elegant way that you can sort of, it amounts to duplicating just the ECC check itself. If you're interested, you can come find me afterwards. But at Andy's, we call it EDC after ECC, which just means that we actually do the ECC a second time to make sure that the ECC itself is corrected. I don't need it in an ASIL D system because when I have dual core lockstep, I've got 2 of these anyway. But in an ASIL-B system, this is quite valuable. But it's not just about ECC on those RAMs. What happens if the way a RAM works is I get an address in, there's a giant decode that decodes that into a certain row, and what if that decode is wrong? If I'm accessing the wrong location in memory, but the ECC is obviously still correct for that location, I've read out incorrect data and the ECC actually matches, I wouldn't detect it. So there can also be a failure where internal to the RAM, it doesn't even access the location. That tends to look like all zeros or possibly all ones come out. Both of these things can be corrected just by having two different RAMs, one for your data, one for your ECC code. The reason to have that is that then if you have a single failure in one of those decoders, it's not in both of those decoders, and you will detect those sorts of errors. So this was fascinating to me when I first read about it, and also the EDC after ECC, because you realize as you go through to get compliance on your CPU core, these individual places seem small, but they have a very large impact on your total coverage. And by the way, to get this coverage, you have to go through an outside company, and it's quite involved, a lot of math, and so you detect these problems, and you definitely realize how important it is to have these things. And if you can come up with an elegant solution that doesn't add a lot of area or power, then that's what you want to do. All right. Okay. I'm throwing a lot of stuff at you guys. Hopefully, so my next slide actually talks about that. So I talked in the beginning about sort of systematic faults and then random faults. One of the things you want to look for in your IP vendor as well as your software vendor is a certificate for the design process. If you have a software error, there's no such thing as a random software error. It's either bug-free or it has a bug. In hardware, you get these random faults. But in hardware, it can also have bugs. So you need to make sure that your hardware design team has gone through this certification to make sure that their design process is also ASIL-B or ASIL-D certified. Andy's actually went through that, I think it's more than 5 years ago now. And as you can see from the presentation earlier, we actually have a lot of cores from ASIL-B up through ASIL-D levels of coverage. And this is all certified by outside reviewers. So it's not the vendor, it's not Andy's that says it's certified. In this case, it's TUV, TUV. I alluded in the beginning that it's not enough to think about the CPU subsystem. I'm a CPU designer. I spent most of my career designing CPUs, and another big part of my career designing large SoCs. When you're designing a whole system, it's not just the CPU, it's the software running on the CPU, but it's also the rest of the chip. So is it good enough just to know that within the CPU I've got dual core lockstep, I know that it's executing the right stuff? What if the path out to memory through my interconnect? What about the memory controller? What about the DRAM itself? You have to think about all of this stuff, and that's not necessarily your CPU vendor's problem, but your CPU vendor is a key partner in enabling you to build that totally protected ASIL-D certified system. So you have to think about going outside of the CPU. From the CPU point of view, this is mainly going to be your bus interface. We can't really duplicate buses. If you think about it, it kind of doesn't work. There's probably ways. but there's better ways, and that's what I'm going to talk about in the next couple of slides. So first of all, it's easy for the bus data and address. You can add parity. Same kind of code that you have for the RAMs. You can do error correction. You can do double error detection. It turns out it takes about 8 bits across a 64-bit word. It costs more if it's on a smaller piece. So the way we solve that is for the control signals. For instance, if you have an AXI bus, we group all of the things for one channel together so that we can share those parity bits. We actually, on Andy's cores, we don't group the valid and ready signals. We actually just duplicate them, or we actually have a parity bit for them. So we actually, it's always the opposite encoding. So a 0 has a parity bit that would be a 1. The reason we do that is valid and ready are just too important. If you get a problem with a valid or a ready, it's gonna cause a major problem. It's almost certainly gonna cause a bus lockup. So we just duplicate those signals, and there's not that many of them, so it's worthwhile. Note that all of this stuff should be transported through your NOC, through Arcturus or Baya or what have you. Pretty much all the modern NOC vendors have sideband signals that can transport along with any of these channels. The NOC itself doesn't necessarily need to do this parity checking. Ideally, you want it to transport them all the way to the endpoint, and then at the endpoint, it checks all of those parity bits were correct. Some of that's not quite true. The valid and ready, the NOC has to do that because it's really a point-to-point, say, on an AXI interconnect. But you want it to be transported as far through the system as possible, potentially all the way to your, for instance, your memory. We at Andes have additional bus protections, unexpected transfer detection, even odd beat indicators, and again, transaction timeouts, kind of like a freeze detection on the bus. So all of these things are kind of working together, and they're overlapping. All of these techniques work together to give you that high level of coverage, ASIL B or ASIL D. There's actually other things that aren't specific to ASIL D that are very helpful. We have core trapped status indicators, which basically just says you can sensitize outside logic. If you know I'm not expecting any exceptions or interrupts at this point, then you can sensitize it to that, because our core, if you got an interrupt and it was unexpected, that's a problem, right? So it's a simple thing, but you have to think about it, and your CPU vendor has to provide it. Memory protection is pretty standard for all RISC-V CPUs, but this also helps. MMU checks, PMA checks, PMP checks, ePMP checks. All of this stuff contributes to your ASIL D coverage. So I put a picture of a car here because it really is, all of this stuff has to go together. It's the CPU, it's the SOC, it's the software, and this is very difficult to do. You definitely need these overlapping solutions, and it has to go all the way to the endpoint. So I hope this helps you understand why, when you're driving down the road, that your car, even if there is a fault, it's going to recognize it because these systems have been certified as compliant to those levels. Thank you.